we have been discussing the fundamental concepts. In that we have discussed the continuum hypothesis and then the two different approaches for describing fluid flow. Now we are going to discuss a special derivative which is characteristic of continuum mechanics and transport phenomena, I would say, what is called a substantial derivative. Now of course other topics follow later on. Okay. To begin with, we look at the types of derivatives which are familiar to you. The partial derivative, which we indicate as dou by dou t, the total derivative d by dt. This should be familiar to you from your calculus course. Now a new derivative which is represented by capital D by dt, which will have a new physical significance. Now as you go along the course, you will understand where is it used, how is it used, you will have a better feel for the physical significance, but right now to give a quick motivation, suppose if we extend Newton's second law of motion for a fluid particle, we know Newton's second law for a solid particle, suppose we extend for a fluid particle, then we would write the Newton's second law as the force acting on the fluid particle is equal to the mass of the fluid particle multiplied by the acceleration of fluid particle. What I have done is express the well known Newton's second law of motion for a fluid particle, which you would have written so far many times for a solid particle. Now just to tell you that this acceleration of fluid particle can be expressed in terms of this new derivative, which we are going to call a substantial derivative. Okay. Right now that is the motivation. As we go along the course, we will use this derivative several times and several places, you will understand as we go along. Okay. So as I told you, the name of the derivative is substantial or material derivative. Let us define it first before discussing it and deriving expression for that. So how do you define? It is the rate of change of a property. When I say a property, it could be velocity, temperature, concentration of a fluid particle. By this time we are familiar with what a fluid particle is, we have discussed in detail, we will be able to visualize it as it moves through the flow field, okay, and as seen by one moving along with the fluid. To have an example, I have shown here the converging nozzle which I had seen earlier. So now we have considered several fluid particles here and they move along the length of the converging nozzle. Now suppose if you take one fluid particle and then follow its motion, what is the rate of change of its property? So rate of change of a property of a fluid particle as it moves through the flow field. So how do you imagine? Suppose if you sit on the fluid particle and go through the region of flow, what is the rate of change of the property which you would experience? Could be velocity, in this particular case it's velocity, it could be temperature, it could be concentration. Okay. We will take two examples. First we will take velocity as an example for a property, then we will quickly analogously do for temperature, just to show you that this substantial and material derivative can be applied for any property. Usually what is discussed is velocity and extended for other properties as well. We will discuss both for velocity and temperature. So why this particular example of converging nozzle? As we have seen earlier, as the fluid flows along the length of the converging nozzle, because of the reduction in the cross section area, there is an increase in velocity. So from the fluid point of view, it experiences an acceleration. So if you are sitting on the fluid particle and traveling along with it, you will experience an increase in velocity, and that is why this particular geometry, this configuration has been chosen here. What we are going to discuss applicable for any general case, to visualize, to understand, we have taken this particular case. Okay. So as a property we will take velocity as an example. Okay. Now, we want to find out the rate of change of velocity of the fluid particle, which is of course the acceleration of the fluid particle. And how do you define? Because it is a particle, just extend your particle mechanics knowledge of expressing the acceleration of fluid particle in terms of derivative of velocity of the particle. Okay. Velocity is a vector here and acceleration is a vector here. Okay. So, we have expressed acceleration of particle as the time derivative of the velocity of the particle. This is exactly what you would have come across in your particle mechanics course. Only difference is here the particle refers a fluid particle as been discussing so far. Now, what we now use a physical principle at any instant of time. Suppose let us say you are somewhere here, which means you are travelling with a particle and you are at some position here. Okay. Now, the velocity of the fluid particle at that position at that particular instant is equal to the velocity of the fluid in that particular location. Okay. So, what is the implication of this? The left hand side is from a Lagrangian viewpoint, we are telling from particle viewpoint velocity of a fluid particle. Right hand side what we have, please note the word here velocity field. Okay. We have already discussed that moment I say field, it represents a Eulerian frame of reference. So, why is it local value? We are at a particular position at a particular instant, the fluid particle is at that particular location, its velocity should be equal to the velocity of the fluid at that particular location. Okay. That is what is represented here as an expression x, the particle position of the x coordinate of the particle at that particular instant, similarly y particle, similarly z particle. Okay. So, looks like a very simple statement, it has a very key importance, connects a Lagrangian viewpoint to a Eulerian viewpoint. Why is it Lagrangian? Talking about a fluid particle here, but talking about a velocity field here. Okay. Simple intuition will tell you the particle is representative of the fluid. So, at a particular instant at a particular position, the velocity of the fluid particle should be same as that of the fluid, okay, given in terms of velocity field. If you want to write this in expression, velocity of the particle, okay, is equal to the velocity in terms of Eulerian field at what is the location? Location at which the particle is present. Left hand side is velocity of the particle is equal to velocity given in the Eulerian field, not at any location, at the location at which the particle is present, given by the coordinates x particle, y particle and z particle. Okay. Now, we said the acceleration of the particle is given by the derivative of the velocity of the particle, and now we have used a physical principle and said that the velocity of the particle is equal to the velocity of the fluid at the position of the particle. This is what we have seen in the last slide. Now, I will substitute in this place, instead of velocity of the particle, I will substitute this velocity of the in terms of Eulerian field. So, dV particle by dt is equal to dV by dt. V is a function of x particle, y particle and then z particle and of course time as well, okay, divided by dt. Okay. So, left hand side what we have is velocity of the particle, right hand side you have velocity in terms of Eulerian field, and it is a function of x particle, y particle, z particle and time. What you have on the right hand side is a total derivative, and of course we know by chain rule how to express a total derivative in terms of partial derivative. I would like to repeat this. Right hand side you have a total derivative and it is a function of 4 variables x, y, z of the particle and time, and using chain rule we express in terms of the partial derivatives. So, the independent variables are x, y, z and t. So, first we differentiate v with respect to time and then dt by dt, which of course is unity. Next we partial differentiate dou v by dou x particle. What do we mean by partial differentiation? For example, here when I differentiate with respect to time, x, y, z, all the 3 coordinates are kept constant, which means at a particular location. So, when I say differentiate with respect to time, then partially all the other 3 spatial coordinates are fixed. So, this represents the derivative at a particular position. Okay. And now, when I differentiate with respect to x particle, I keep the time constant and the y particle and z particle constant. So, there is we are considering variation of velocity with respect to in the direction of x direction. Okay. Now, of course, then we have dx particle by dt. Why is it d by dt? Because these coordinates, the position of the particles, the x, y, z coordinates of the particles are functions of only time. So, that is why this is the d by dt and not it is not dou by dou t. Here it is dou by dou t because b is a function of 4 variables. They are partially differentiated in respect to only x particle, keeping all others constant, resulting in a partial derivative. X particle, y particle, z particle are all locations of the particles along its trajectory, and hence depends on only time, and hence we have d by dt here. Okay. Analogously in the y direction, analogously in the z direction. Okay. Now, what is shown here is a fluid particle at a location x particle and y particle. In a time instant from t to t plus dt, it moves to another location where x particle plus dx particle, a small displacement, okay, dx particle and y particle plus dy particle. So, this gives the position of particle at, let us say, t. This gives the coordinate of the particles at t plus dt. Now, if you take the rate of change of x coordinate with respect to time, you will get the velocity of the particle. Okay. Dx particle by dt is equal to the velocity of the particle in the x direction. Okay. That is how we define the velocity. Now, we have already seen that the velocity of the particle at a particular instant, particular location is equal to the Eulerian velocity, and that is why I have used here Vx. Dx particle by dt gives the velocity of the particle in the x direction. We have seen that at any instant the velocity of the particle is same as the velocity of the fluid, but now I use the x component of the velocity of fluid given by the Eulerian description. Similarly, in the y direction and similarly in the z direction. So, in these expressions we are going to replace this dx particle by dt in terms of the velocity field x component of velocity of the fluid given by the Eulerian description. Similarly, Vy and then similarly Vz. Okay. Now, here we have the x particle location, y particle location and then z particle location. Now, once again, just like we express for velocity, we will use the physical picture that the material position vector. Why do I say material position vector? Because I am following a material particle, its position is given by the material position vector denoted by x particle, y particle and z particle. So, material position vector of fluid particle in Lagrangian frame is equal to the position vector. Why do I say position vector? Position vector is just like our usual x, y, z coordinate in the Eulerian frame. When I say x, y, z, it is in Eulerian frame. When I say x particle, y particle, z particle, it is in the Lagrangian frame. Okay. So, once again we replace this x particle, y particle, z particle with x, y, z. So, we are going to make two replacements. One is that these derivatives will be expressed in terms of the velocity of the particles and hence in terms of velocity of the fluid in the respective directions, and then similarly these coordinates of the particles, they are material coordinates. Why do I say material coordinates? As I told you, they are position vector of the particle as it flows through the flow field. I am going to replace that in terms of the Eulerian spatial locations. Okay. Okay, let us do that. So, this is the expression which we have written for acceleration of the particle, and then we wrote in terms of the total derivatives expressed in terms of the partial derivatives. This is for the x direction, this is for the y direction, and then similarly for the z direction as well. Okay. Now, we have seen the time derivative of the x direction coordinate is the Vx, and similarly the y direction we have Vy, and in the z direction we have Vz. Okay. So, we will make these substitutions. The acceleration of the particle, now the acceleration of particle is a function of x, y, z and time, okay. And this total derivative, this special total derivative as a new representation which we say as capital dV by dt. So, moment whenever you come across capital dV by dt, it represents the substantial derivative. Why substantial derivative? We are following a material or a substance and hence call substantial derivative or material derivative. That is the reason for the name substantial derivative, material derivative. Okay. What is it we have done? We have dou v by dou t here, dt by dt is 1, okay. And now dou v by dou x particle is here, and instead of x particle I have used the Eulerian spatial location x, and dx particle has been replaced with Vx here, okay. So, this expression becomes, this term becomes Vx into dou v by dou x. Similarly in the y direction, similarly in the z direction. Now, left hand side I would like to repeat the acceleration of the particle. Remember it is a vector equation, acceleration is a vector, these velocities are all vectors here, and these are components of velocity in the x, y, z directions. So, if you write v vector is equal to Vxi and then Vyj and then Vzk, where I, j, k are the unit vectors, this x component of the velocity field, y component velocity field, z component velocity field are what are appearing on the right hand side, similarly the derivatives. Okay. And okay, remember this has a good significance, acceleration of the particles from a Lagrangian viewpoint, but that is expressed in terms of the Eulerian spatial location. X, y, z are our usual coordinates, but this is the rate of change of velocity as you follow the fluid particle, which means it has a Lagrangian meaning attached to it, but it is express a function of x, y, z in the flow field. Okay. What I have done next is, because the vectorial equation it has, you can write 3 components of it. I have written the x component here, instead of a I have written the, just like this you can write an equation for acceleration, okay. V is a vector here. Similarly, you can write the a vector in terms of ax, ay and then az, and of course I, j, k, etc. So, ax is the, ax particle is the x component of the acceleration of the particle, function of x, y, z and time, and I just written instead of v vector Vx, similarly Vx here. So, I have replaced everywhere the vector with the x corresponding x component. So, this gives the acceleration of the particle in the x direction as a function of x, y, z and time. Now, what is the most important significance of this expression? Okay. Given the velocity field which we can easily measure, okay, it is an Eulerian description. We already seen that the Eulerian measurement, Eulerian description is more practical. So, given the velocity field, we are finding acceleration of a fluid particle as a function of the Eulerian position. This nicely combines the Lagrangian viewpoint and the Eulerian viewpoint. Acceleration of fluid particle, why it is Lagrangian? Because the rate of change of velocity as you sit on the particle and follow it, that is why acceleration of fluid particle represents a Lagrangian variable. V is a Eulerian field, because a function of x, y, z and time. So, if you have a velocity field, if you measure velocity at different locations, you can find out what is the acceleration experienced by a fluid particle at different spatial locations. Okay. That is the biggest advantage of this expression. Remember we said the independent variables for Lagrangian description are the initial position and time r naught and t. Okay. So, if you have a velocity as a function of r naught and t, you can differentiate that and then get the acceleration, but usually we do not have access to that information because that requires Lagrangian measurement. What we have access is to the velocity field information, but using that you are able to get the same meaning as a Lagrangian derivative. Okay. So, dv by dt, as I told you, is called the substantial derivative, also called as material derivative. In this particular case, it is the substantial derivative of velocity, okay. And because it is substantial derivative of velocity, it is also called as the acceleration, okay. Because substantial derivative of other variables do not have any special name, because it is velocity we call it as acceleration. Okay.